Okay, this is going to be probably the fastest covering of Chem 1 topics ever in the history of the world. We're going to cover like 5 days in 40 minutes, mainly because every single bit of it is review. Okay, so I gave you guys a new periodic table, and I want you to mark that up, and you also need out your notes because your notes have the problems that we're going to do. Let's just reintroduce ourselves to this periodic table. So the periodic table is broken up into different groups or families, as well as different energy levels. N being the principal quantum number, being the energy level that we're looking at. Okay, and so those are indicated with these numbers 1, 2, 3, 4, 5, 6, 7. Now the groups, as we go across, have some names. Let's review. What's this group 1 called? Alkali metal. Group 2? Alkali earth. All of these guys in the middle, transition metals. And we go over here to, there's the nitrogen group. The oxygen group has a funny name, which no one ever talks about, but you learned it in pre-AP. Chalcogens. These are, fluorine group is the halogens, and the helium group is the noble gases. Down here we have our inner transition metals or rare earth metals. Okay. Now, what's also really important is how the periodic table is blocked, because we can associate it with sublevels or different orbital types. So on the next slide, you guys don't have this, but let's just review the different orbital types that exist. On every level, we have a set of sublevels. Okay? A sublevel is a set of orbitals. These are our different possible sublevels. Some levels have 1 sublevel, some levels have 2, and some levels have 3 sublevels, and so on. So this first sublevel, what is that orbital type? It is the S. And that S orbital holds how many electrons? 2. Any orbital holds 2 electrons. Remember that, right? But because there's only 1 orbital on the S sublevel, the entire S sublevel can only hold 2 electrons. How many orbitals are on a P sublevel? Here's our P's. 3 orbitals, right? Now, some people say these are like dumbbell shapes, so you're going to see them differently. Sometimes they make them super skinny. Sometimes they make them just big fat circles. But if you've got 2 lobes, it's going to be a p orbital. So in every p orbital, we can hold 2 electrons. So how many total electrons can we hold in the p sublevel? 6. 2 electrons in each. Okay? Those are the Ds. The Ds, and all these orbitals differ just by their orientation. Like there's a px, a py, and a z. Well, this would be the py, and this would be the pz coming at you. So they are just different orbitals based on their orientation in space. So the D sublevel has 5 orbitals. So how many electrons can be under the D sublevel? 10. So our D sublevel holds 10 electrons. Those crazy Fs, those are out of control. There's 7 of them. So how many electrons are on the F sublevel? 14. Now, if you look at those numbers, 2, 6, 10, and 14, those correlate directly to the periodic table. Do you remember your S block here? These are your S's, right? And then your P block. Helium actually belongs in the S block, okay? And your P, remember, had 3 orbitals, 6 possible electrons, 1, 2, 3, 4, 5, 6. This was your P block, right? And then what block was this? This is not a rhetorical question. I heard 1 person out of 30 say the letter D. And then this is your S block, okay? And let's take a look now at the correlation between number of sublevels on a level. There's a pattern here. On level 1, we only have 1 sublevel. And what is that sublevel? S. On level 2, we have 2 sublevels. And what was that? S and P. Now, it doesn't look like we have 3 on level 3, but we do, because Who remembers anything about the D energy levels? It's 1 under, right? It's N minus 1. So your Ds actually start, this is on the main group elements level 4, but when you get to this D block, it drops to 3. So on level 3, there are 3 sublevels, an S, a P, a D. How many levels do you think are on level 4 then? How many sublevels? 3. There's a pattern, guys. Level 1, there's 1. Level 2, there's 2 sublevels. Level 3, there's 3 sublevels. So level 4, there might be 4 sublevels. There are our S, our P, our D, and our F. We have a 4D and a 4F. This right here, on level 5, this is the 4D. What were the Fs? And minus 2. So at level 6, our 4s started really on technically level 4. Because if you look where they're inserted after main group S6. They're inserted right here. So that's a level 4. So on level 5, there's theoretically supposed to be 5 orbital types. We just don't know them yet. According to the quantum theory and quantum numbers and all that jazz, there should be a G. They talk about G. We just don't know about G right now. So there is that connection. Now, one other thing I want to get y'all to come up with is how do I determine how many electrons are on any sublevel? I'm sorry, on any level. There was a formula. On level 1, how many electrons? 2. This is N1, this is electrons. On level 2, I have 8. On level 3, I fill the S, the P's, and the D's. How much is 18? Can y'all come up with a formula, Naira? 2n squared, and you need to know that. To figure out how many electrons on any level, you need to know 2n squared, because they could give you a theoretical level of 25, and you have to figure out how many electrons could be on that level. That's a common thing the AP asks. So you need to know 2n squared. Okay? So let's go ahead and answer some questions here. What is the maximum number of electrons in a 2s subshell? That's the same as saying sublevel. On the 2 level, there's an s orbital. How many electrons can be in that? 2. The 3d sublevel. How many electrons? Electrons? How many orbitals on a d sublevel? 5. So how many electrons? 10. The n equals 4 shell. How many electrons? That's an energy level. How many electrons? 2n squared. So that's equal to 32. Watch the language. 2p orbital. 2. In any one orbital, you're only going to hold 2 electrons. On any sublevel, you're going to hold as many electrons as number of orbitals you have. Okay? So if you have a p sublevel, that's 3 orbitals, so that's 6 electrons. So you got to watch the verbiage there. Okay? All right. Next. Now we're going to look at I'm going to draw some diagrams, and we call them orbital spin diagrams. And in doing so, we'll hopefully help remind you of these 2 rules, the Aufbau and the Hund's rule. So this right here, what's that called? I mean, it's important for you to know what things are called, so when you get a question, you know what you're supposed to write about. Who remembers what this is called about oxygen? Go ahead, Scott. Jacob. What's it called? This is the electron configuration. Okay? We're going to review how to do this today, but whenever you're asked to draw a diagram, some people call it orbital spin, some people just call it spin, some people just call it orbital diagram. All of those mean the same thing. And you're going to draw a box for every single sublevel. Okay? So I think I have on the next slide it broken down for you. So, how many orbitals are on a 1s sublevel? 1. So we're going to draw one box. How many on the 2s? 1. And how many orbitals on the 2p? 3. So we're going to draw our orbitals, right? And now we're going to fill them in with electrons from the electron configuration. How many electrons are in the 1s? 2. That's what that 2 means. So we're going to do up and we're going to do down. Okay? They have to be opposite spins. On the 2s, how many? 2. We're going to do up and we're going to do down. And in the 2p, we have how many to place? 4. How do you place them? Up first in all, like in together, and then how do you want me to put them? 1 in each, and then double up. So the rules that apply to some of these things, and I'm just going to kind of do some scratch work. If we have a set of p's, we have to place them up singly with the same spin. So if we do that, that's a violation of Hund's rule because we're not placing them with the same spin. Another violation of Hund's rule would be doing that. You have to place them singly first. This is a high energy state because this is experiencing repelling forces when it doesn't have to. The other electron could be in this orbital and not have repelling forces. So that's possible, but it's just a higher energy. As is this possible, but it needed some energy to flip that electron to that point. So these are excited states. Okay. Another thing that's wrong is if you see this. This would be 2s. This will be 2p. If you see this, that's an excited state. What did we do wrong there? We didn't fill up the s's. The s sublevel has to be filled. You have to fill your sublevel before you move on to the next sublevel. And if you don't, that's an Aufbau violation. Boyer, to build in German, it's building from low to high. So you've got to follow filling order. So anytime you see something like that, and we're going to practice these at the end of the lecture. Okay? So let's review what valence electrons are, and then we'll get into electron configuration. Valence electrons are the outermost electrons. So here again is the, oh, this is not oxygen. This is neon. This is the electron configuration for neon. So when they ask you for valence electrons, we look at the outermost shells because that's where valence electrons come from, the outermost energy level. So how many valence electrons do we have? 8, the 6 and the 2. Okay? You're going to need to know valence electrons for a lot of reasons when we get into drawing Lewis diagrams and all those things again that we're going to hit next unit. So what I want to do is make sure we know how to determine very quickly from the periodic table using the Roman numerals. Okay? Energy level, group 1 has 1 valence electron, right? Group 2, 2. Go to the aluminum group, 3. Carbons group, nitrogens group, oxygens group, fluorines, and the noble gases, 8. You're going to need to know those, and the Roman numerals up top tell you that. Now, what about all these transition metals? This is the one that throws people. They all have the same number of valence electrons. Can anyone tell me what those are? JD? Okay, exactly. They are all 2 valence electrons. Can you explain to me why all are 2? Correct. Perfect. So let's say we were looking at vanadium. Okay? Vanadium would have everything up to argon, and then it would be a 4s2, and then a 3d something. Who cares? 4 is higher than 3. So no matter what noble gas we're going to be at, there's always going to be a 4s2 above it. Same thing for every single group, including these. So all the transition metals and all the intertransition metals have 2 valence electrons. Everyone get that? Okay. So electron configuration. Unless I tell you otherwise, you can use the noble gas configuration, where you go from the noble gas on the level prior to the element we're looking at and then continue from there. However, on the AP, I've seen it multiple times, like alternating years, where they will actually say write the full configuration, and then they put in parentheses 1s2, 2s2, ... Does everyone understand that means write the full configuration from the beginning? Okay? And we did get like tons of people just putting noble gases in parentheses, and I'm like, nope, no credit. We couldn't give them credit. Okay? So you got to read your instructions. So we're going to build through all the elements. We're going to put the D's one below. We're going to put the F's two below. And we're just going to use our finger and go through and do our electron configurations, starting with sulfur. We're going to do full for these two. But after that, we will do them all shortcut with the noble gas, or they also call it core configuration. Core meaning core electrons. So starting with 1s2, and I want to hear you loudly. I want them to be able to hear you at home. Let's do our sulfur. 1s2, let's go. 2s2, 2p6, 3s2, and then 3p4, right? We go through every block. So we first state the level, then we state the sublevel, and then with an exponent, how many electrons are in that sublevel. This has to be a big number, a letter, and then an exponent. Got to be able to tell those apart. All right, barium. Barium is quite a ways down. Yes, we are doing full. It's going to be painful, but you'll never have to do it again. If you know how to do that, you're good to go. So barium, let's start out. 1s2, 2s2, louder, p6, 3s2, 3p6, 4s2, be careful, 3, good, 3d10, good, good, 4d10, 5p6, then 6s2. Yeah, that was gross. But when you do the noble gas configuration, I will allow you to do xenon and then 6s2. A little bit easier. Well, and why is this an okay thing to be considering? Why do we care? Why don't we care about all this mess? They're not valence electrons, they're core. These valence are going to determine the type of reactivity we're dealing with barium. Okay? So EU, from here on out, let's go ahead and do shortcut. EU is where? It's an intertransition metal right there. So this is inserted on main group level 6. So we need to put xenon again in parentheses. And then what do we say? 6s2, 4f, and then count across. That's it. The f's come before the d's on that level. If we were to continue, we'd be 4f14, 5d10, right, and then 6p6. All right, so we're just going to write the core configuration. We're not going to write show the core configuration. All right, so magnesium. No, just core. So neon, 2s2, 3s2. Good. All right, krypton. I know you want to put it in brackets. No. You got to go to the noble gas before, and it's argon, and then good. 4s2, 3d10, 4p6. All right. Rhodium, RH. Where is that sucker? 45. So krypton again. RH. So it's krypton, and then 5s2, Is it 7? 4d7. Okay, and then what's next? I'm really lost today. Platinum. It's xenon, right? And then 6s2. Be careful. You got to put in the 4s. You can't just skip, oh, there's no Fs. 4f what? 14. And then what? 5d 8. I'm trusting you that it's 8. Because I can't see it from here. And last but not least, bismuth. It's on the same, it's main group 6, which is just kind of close to that platinum. So it's xenon, 6s2, 4f14, then what? 5d10, and then 6p3. Okay, so if I were to go to all of these and ask you valence electrons, you could tell me, right? How many valence electrons in bismuth? 5, right? We got to look at the 6s. That's important. Okay, moving on. Y'all are doing good. Now, we're going to have to determine if something is paramagnetic or diamagnetic. Di means 2, right? So if all the all electrons are paired, all of them, it is diamagnetic. They're all together with something. If there are any, 1, 2, 3, 4, any unpaired electrons, we call it paramagnetic. That leads to solutions having, ion solutions having colors. It leads to things literally being magnetic in species. So let's draw an orbital diagram for silicon. So drawing an orbital diagram, what do I expect from you? So in your orbital diagrams, you do not have to draw anything but the valence shell. So in silicon, we're going to, where is silicon? It's on number 14, right? So we kind of have neon here. We're going to ignore those electrons. And then what do we have? We have an S and a P sublevel. So what S sublevel is this one? To get to silicon. Is it 3? 3S. And then what is this P sublevel? 3P. And the P's have 3 in their set, and the S only has 1. So to get to silicon, how many electrons do we have in the S? 2. And how many do we have in 3P? 2. And we're going to follow Hund's rule, and we're going to go up, up. So you can get asked a lot of questions. How many valence electrons? How many? 4. How many unpaired electrons? 2. If there's unpaired electrons, what do we call this? Paramagnetic. Okay? All right. Like everything in AP chemistry, we're going to have some exceptions. The exceptions to E configuration are as follows. There's 2 exceptions, and it's the chromium family, meaning chromium and molybdenum and tungsten, and the copper family, meaning copper, silver, and gold. You have to recognize that. So let's start with chromium. Chromium, tell me its expected noble gas configuration. We have argon, and then what? 4s2, 3d4. Well, that's actually not its ground state configuration, okay? Due to the fact that the energy difference between S and D, the S sublevel and the D sublevel is super small, super tiny, okay? So because it would be like me stepping from here to here. Not much of a big deal. It's actually a tiny drop because we're getting slightly, a teensy bit closer to the nucleus. The D's are right under that 4s. 3D's are. So what happens, because of that fact, and because there's such a low energy difference, we're actually going to go fill that D sublevel with one of the S's. So chromium's actual electron configuration is that. So chromium actually only has 1 valence electron. So this is not correct. So this happens with anything with a D4. on any energy level. Okay? Copper, same exact situation. We have argon, 4s2, 3d9, right? That's what we'd expect it to be. But what actually happens, that S is going to let it loose and fill this D9. So it happens in the D9 and the D4 family. Now, one thing I want to make clear, it doesn't happen from S to P. So if you have a P2, you're not going to move an S, because that's equivalent to me trying to jump over the Grand Canyon. Can't do it. Too much of a big energy differential. So it only happens from S to D. And we never see it in the Fs, even though it probably happens in the Fs as well. They never give us those examples. Okay? Any questions? Y'all are awfully quiet. All right. These are fun configurations of ions. They're easy. When atoms become ions, they're going to lose or gain electrons, right? With the intention of becoming like what? 8, having 8 filled. So they're going to end up being isoelectronic for the most part, isoelectronic with a noble gas. So your job is to figure out, okay, what noble gas are we becoming isoelectronic to? So sulfur, -2. Find sulfur on the periodic table. To become a -2, what's it going to do? Gain 2 electrons, making it isoelectronic with what? Argon. So we're going to write the electron configuration for argon. NBD. No big deal. So we are at 3s2. I wrote neon. 3s2, 3p what? 6. So that's pretty easy. And then Al plus 3, in order for it to become a plus 3, what is it going to do? Lose 3 electrons, making it isoelectronic to neon. So neon is 1s2, 2s2, 2p. You could put helium in parentheses, but it's faster to write 1s2 than parenthesis helium parenthesis. Does everyone get that? I want to draw those eyes, that emoticon eye. Are the pupils on the same left side? Okay. You got to watch out here, folks, because I've graded one of these, and it is pathetic how many students miss this. All right. When iron becomes charged, there's something we got to be careful of. So what I want from you right now is just, what's the straight-up configuration of iron neutral atom? Tell me the noble argon, okay. 3d6, okay. When things become charged, they have to lose their outermost electrons first, okay. So you're not just going to go to iron, pluck off 3, and go, oh, 4s2, 3d3, I'm done. No, you're not. Okay? If we're making iron plus 2, we can do that first. Argon, what's the valence shell there? The 4s. So we're going to lose the 2 electrons out of that, leaving me a 3d6. So if iron is a plus 2, it's going to be 3d6. Iron can also be plus 3. This is actually really cool. Like, we used to be a little more hardcore in teaching this. We're getting easier because it seems like expectations are lowering for students. But it really is. It's kind of sad. If we lose an additional 1, we still lose those 2 S's, but we lose an additional D now to get 3 lost. Y'all see that? Why this is cool, if you think about, oh, it's D's. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is kind of cool if you look at it this way. 2, this is a 4s and this is a 3d. Iron commonly becomes plus 2. Why? It's going to get rid of its valence, right? Why is getting rid of an additional one to make +3 a cool thing, a good thing? Exactly, we're alleviating repulsive forces in that particular orbital. So because of that, that's the reason iron wants to do that as well. Think about copper and chromium. Copper can be +1 or +2. What's copper's real electron configuration? S1, D, whatever, right? Because it didn't move it. So that's where copper gets its +1. So there's reasons behind all those charges that we make you memorize. Okay? Do you have to know those? No. We don't require that anymore. But you do need to at least know how to write the configurations for a given ion. Does everyone get that? So you can't willy-nilly go and just go to a metal and take away electrons. Don't let yourself do that. You have to stop and ask yourself, is it a transition? If it is, I got to just take away valence first. So we're going to practice. We already kind of talked about these. The only one we didn't really mention was the Pauli exclusion principle, and I'll talk about it when I get there. So you're going to tell me if this is an excited state or a ground state, or if it's just impossible, and what violation it is. So looking at this first one, is there anything wrong with that? Huh? Nope. This is ground. All right, this next one, what's wrong? This thing is turned, right? So this is an excited state, and it's a violation of Hund's. This is the one we didn't talk about. These two electrons, for all intents and purposes, are the same electron. They're on the same energy level, they're in the same sublevel, they're in the same orbital, and they have the same spin. They're the same electron. You can't have two of the same electrons. So this is actually impossible. And this is Pauli's exclusion principle. That's what Pauli's exclusion principle says. The true definition is no two elements can have the same 4 quantum numbers, which is basically what we just talked about, energy level, sublevel, which orbital, and spin. Okay, what's wrong with this one? Excited, and it's a Hund's violation. Okay, next. Yep, impossible. Two of the same electrons in the orbital. Pauli's exclusion principle. All right, this guy. Oops, someone got it. Is that you, Warner? Why is it ground? Oh, who was it? Was it Matt? Sorry. Matthew, why is that ground? That's right, ground because this is the chromium family. He caught it. Now, if this were the P's, it would be Aufbau, because we'd have to fill the S first. What about this one? Oh, I just told you. This is excited. We should have filled this S before moving on, because this doesn't exist in the P's, so this was an Aufbau violation. Any questions? Okay, let's work on your homework.